Alright, so far we looked at the distribution of a single variable and we made inference about its population parameters. So in this video we will learn how to examine the relationship between two variables. For example, relationship between height and weight of a group of people. And to answer this type of question we use a correlation analysis. So correlation analysis is used to examine the strengths and directional relationship between two variables. Please note that correlation doesn't imply causation. It's just a measure of association. It doesn't mean that there is a cause and effect relationship between two variables. So we have two main types of correlation analysis. Pearson product correlation, which is a parametric test, and the Spearman rank correlation, which is a non-parametric alternative for the Pearson product. In a separate video in this channel, we compared parametric tests and non-parametric tests with details. So in this video, we will first learn the characteristics of each technique for Pearson and also a Spearman rank correlation, and then we will use our programming language to solve real-world examples. Pearson correlation is used to measure the linear statistical association between two continuous variables. In other words, when the variables are interval scale or are in the ratio scale. Pearson product provides the information on the strength and sign of the association or direction of the association. So before running the Pearson correlation, you have to check three important characteristics. First, both variables are in continuous scale. So for example, we cannot use Pearson correlation for ordinal data. So for example, when your data are like low, medium, high, very high, so you cannot use Pearson product for investigating the association. So both variables have to be on a continuous scale. And also both variables should have normal distribution. Okay, so we will use QQ plot and also Shapiro test to test normality of both variables for each variable. And if you want to know more about the normality check, you can refer to another video in this channel. And also the relationship between both variables should be linear. And we will use a scatter plot to check the linearity between two variables. So do not run Pearson correlation without looking at the scatter plot to make sure the relationship is linear, and also checking the normality to make sure both variables follow normal distribution. If the distribution of one of the variable was not normal or both of the variable was not normal, so you should either use transformation such as log transformation or a square root transformation that may lead to normal distribution. Otherwise, you have to use non-parametric version of Pearson correlation, which is a distribution-free test, which is a Spearman rank correlation. And if the relationship between two variables, x and y, was not linear, again, you can use transformation to probably linearize the association, or you have to use non-parametric version. So Pearson correlation is a standardized measure of covariance. And as you know, covariance indicates that how two variables vary together. So positive covariance, it shows that the two variables are positive related. And a negative covariance shows that the two variables are negatively related or inversely related. So we don't want to stuck in hand calculation, and we let the software does the calculation for us. But after you calculate the coefficient for the Pearson product, so the range of values for R is between -1 and +1. So the values that are very close to +1 indicates that there is a strong positive correlation between two variables, which means that if one variable increases, the other variable also increases. The value that is close to -1, it indicates that there is a strong negative relationship between two variables. In other words, when one variable increases, the other variable decreases. And the values that are close to 0 indicates that there is no correlation, or there is a very weak correlation between two variables. Okay, so from this scatter plot, as you can see, when one variable, so doesn't matter which variable is in the x direction, which variable in the y direction. So when x increases, y also increases for all of these, right? So there is a positive correlation. So looking at the scatter plot, we can find the direction of the relationship. But here, this line is called best fitted line. So you can see that the points, when you plot for each pair of the observation, the points are very close to the best fit line. That's why there is a strong correlation. So when the points are very close to the best fit line, it means that there is a strong correlation. They are very close to each other, are highly correlated. So as you can see, there is a very strong and positive correlation between x and y here. But here the points are slightly further from the best fit line. So the correlation, when you look at the correlation, when you calculate the correlation, it will not be very close to 1. It's 0.78, right? So it's less than 0.96. So there's a strong but positive correlation. Here also positive correlation, but the points are further from compared to these two, further from the best fit line. So if you look at the correlation is 0.59, the coefficient, so which shows that it is a moderate correlation. And here, points are even further from the best fit line. So the correlation is kind of weak correlation and between the x and y. And here the slope is kind of a little positive, so that's why you got a positive correlation, but the points are too far from the best fit line. So probably there is no correlation between x and y. And vice versa, here there is a negative correlation, because as x increases, y decreases, right? Here, and for all of them. So the coefficient is going to be negative for all of them. So, and again, you have to look at the best fit line. The best fit line, the points are very close to best fit line. So here we have a very strong correlation, is very close to -1. And here the points are further from the best fit line. So it's going to be, negative, but negative 0.75. It's not like negative, it's not very close to -1. And also here the correlation is less. Here we have a weak correlation, and here we have because the slope is negative, here very weak correlation, or probably there is no correlation between x and y. Pearson correlation measures the strength of linear relationship between two continuous variables. But it doesn't tell you whether the correlation is significant or not, whether at the population level we see the correlation or not. So we must perform hypothesis test of significance to see if at the population level the correlation is significantly different from 0 or not. So as you know from the hypothesis test, null hypothesis always says that there is nothing going on, right? So null hypothesis says that there are no correlation between x and y. And at the population level, the correlation is 0. So if we can reject the null hypothesis, the alternative hypothesis will be there is a correlation between the x and y at the population level. So the next type of correlation is a Spearman rank correlation. And a Spearman rank correlation is a non-parametric version of Pearson correlation. And it is used to measure the strengths of association, but for two ranked variable, okay? So unlike the Pearson product that works with raw data, in this test, first both variables are converted to ordinal scales, which means that you rank the variables separately, which means that the observations are ranked in order of magnitude in a consistent way. So which means if you ranked x in an ascending order, we should do the same for variable y. And after you rank variable x and you rank variable in a consistent way, Spearman correlation measures the association between these two variables, okay? So we normally use a Spearman rank correlation when the normality assumption of both variables couldn't be validated. So there are three important assumptions in a Spearman rank correlation. First of all, there should be at least 5 pairs of observation for significance test. And there should be a monotonic relationship between two variables. Monotonic relationship means that as the value of one variable increases, the value of the other variable never decreases. Or as the value of one variable decreases, the value of the other variable never increases. So here, for example, here we have a monotonic relationship. Why? Because as the value for the x increases, we never see that the value for the y decreases. It never goes down. It can be flat, but it never goes down. So there is a monotonic relationship between x and y, so you can use a Spearman rank correlation. So when you use a scatter plot and you plot them, you will see if there is a relationship like that, it's a monotonic relationship, so you can use a Spearman correlation. And here also there is a monotonic relationship. As the value for x decreases, for the y never increases, always decreases. It can be flat, it's fine, but it never goes up again. But here there's not a monotonic relationship. You cannot use a Spearman rank correlation for this type of a scatter plot, because as the value of the x increases, the y sometimes decreases and sometimes goes up. Okay, so there is not a monotonic relationship, and you can't use Spearman correlation for this type of relationship. Similar to Pearson correlation, the coefficient of the Spearman rank correlation, which is RS, it doesn't tell you whether it is significant or not. Okay, so you need to conduct hypothesis tests. And the null hypothesis for the Spearman rank correlation states that there is no correlation between two variables, but between two ranked variables. Okay, between two ranked variables, there is no correlation between these two variables. An alternative hypothesis states that there is a statistical association between ranked values of x and y. Okay, so now let's move on to the RStudio environment and solve a couple of problems for both Pearson correlation and a Spearman rank correlation. So in the RStudio environment, first of all, let's make a command showing the purpose of the lab, which is to practice a correlation analysis. And so it's better to install ggpopr package because we will use this package to create a scatter plot to visually examine the relationship, whether it's linear or monotonic, and also for the normality check using qqplot. So for that one, we will use install.packages, and here we type ggpopr, okay, and click on run, and after that we can load the package using library commands. Then ggpopr. Okay, so now let's begin with the Pearson product correlation. Pearson correlation. Okay, so first of all, we need to load the data using read.csv file.choose, because we want to select the CSV file, and we need to set the header to true. Okay, so we want to save it in a object called data, and when you click run, it asks me where is the data set that you have, which is here ARM-based data set. So for this data set, if you open up this data set, we have age for almost 49 people. We have their age, and also we have their size of their waist, and also arm circumference. So we want to see, is there any association between waist and also arm circumference? Is there any linear association between these two or not. So the first step is that for Pearson product we need to have the normality check, right? Because both variable should follow normal distribution. So for normality check, the plot that we will use is a GGQQ plot, and for GGQQ plot we have to run this for each of the variables separately. Okay, so we have this for waist because we want to investigate this for waist and also arm circumference, right? So for the waist, if you look at the QQ plot, the points fall along the reference line, right? So it shows that the distribution follows normal distribution. Between our sample and the hypothetical normal distribution, there's a high correlation. And also, if we repeat this test for the other variable, which was arm circumference, and then we click on run, again we can see that there is the distribution almost follows normal distribution. And another way, so in addition to the visual technique for testing the normality, we also use Shapiro test for each of the variable, again data and then for waist. So if you remember, we have to get a p-value that is above 0.05 to not to reject. We have to fail to reject the null hypothesis. So when we run the test, we will see that the p-value is above 0.05, so it means that the distribution follows normal distribution, or it is not significantly different from the normal distribution. And data, arm circumference, run, and also so the distribution for both variables follow normal distribution. So we also have another video about normality check in these channels. If you are not familiar with normality check, so I suggest you to first watch the normality check video. So the next step is that we have to set the null hypothesis and alternative hypothesis. So the null hypothesis always states that nothing is going on, no correlation between waist and arm size, right? An alternative hypothesis states that there is a correlation. Okay, so there is a correlation, statistically significant correlation between waist size and arm circumference. Another assumption for the Pearson product correlation was that we need to use a scatter plot to see the relationship. Okay, so to create a scatter plot, we will use GG scatter. And for the GG scatter, first of all, you have to put your data, and then also tell which variable is X, which variable is Y, and also there are other arguments. But the first one is data, which is our data here. So the variable X is our, so it is arm dot CIRC, so it is case sensitive, and also Y is waist, right? And let me click on run. So apparently there is a linear relationship between the arm and also waist. Okay, so let me add the regression line. So another argument here is add. So here you can add a reg dot line, and if you do that, it will add a regression line. So you can see that there is a linear relationship between the arm and waist. So the normality check was okay, and also there is a linear relationship. So we can also add the confidence interval. So CONF dot interval, we can set this to true. So we can see that so it's a 95% confidence interval for this relationship. So finally, we can use the Pearson correlation test, which is Pearson test. So we will use cor.test command, and the first variable, which was data waste, and then so it doesn't matter which one is first, which one is the second, and the second one is data arm circle. And after that, so we have to mention what type of, because this one is also for the Spearman correlation. So here we have to mention what type of method we are using, which is Pearson, right? And when you click run, so it will tell you that so degree of freedom is n-2, which is 49 minus 247. And look at the p-value. P-value is very, very small, which means that it rejects the null hypothesis. It rejects that there is no correlation between waist and size. So we accept alternative that the correlation, there is a correlation between waist and size. And if you look at the value for the sample, the correlation is almost 90%. And at 95% confidence interval, the correlation is between 82% and 94%. So the value is very close to 1, so there is a strong positive correlation between these two values. So we can say that we are 95% confident that the correlation between arm circumference and waist size is between 82% and 94%. So we can also add this argument to the scatter plot. So for example, we can say COR dot method is Pearson, and also COR dot coefficient, we want to set this to true. So what will happen, it will add the coefficient, and also it uses Pearson correlation, and it also shows you the p-value, which means that the correlation is significant. So at the population level, you can say that there is a strong positive correlation because the value is positive and 0.9, very close to 1. So that's how we can run the Pearson correlation. So remember that for Pearson correlation, you have to always check the normality, you have to look at the scatter plot, there should be a linear relationship, and then you can use the Pearson correlation. So now let's solve a problem for Spearman correlation. Okay. So for a Spearman rank correlation, first of all, we want to use another data set. We want to use the built-in data set in R. So for loading the data, we use data command and also open and close the parentheses. So it will show you the data set that are in the R programming language. So the one that I'm going to use is cars data set that shows the speed and stopping distance of cars. So I want to see, is there any association between speed and stopping distance of cars or not? Okay. So I will use cars here and then run, and then here you have to, when you click on that, you will see the object cars has been added to the environment. So the next step is that we need to check normality, right? Because for both variable there should be a normal distribution, otherwise you cannot use the Pearson product. So Pearson product is always our priority, but if it wasn't possible, we have to use the Spearman correlation. So because we already installed the GG pop R package, so we will use the GGQQ plot, and after that I can, for the variable from the object cars, I'm gonna select distance. Okay, and then when I click run, I can see that, so it is kind of shows that it doesn't follow normal relationship, the distance. So I can also run the Shapiro test for cars and distance. So when I run the Shapiro test, so since the p-value is less than 0.05, so it rejects the null hypothesis. So the distribution doesn't follow normal distribution. So since one of the variable doesn't follow normal distribution, so we cannot use the Pearson product correlation. So our option is that we have to use the Spearman rank correlation, which is the non-parametric version of the Pearson product. So, but again, for the Spearman rank correlation, we still have some assumption that the relationship between two variables should be monotonic, right? So we will use GG scatter plot. So GG scatter, and then for the GG scatter, as you know, so the first one here, the first one is data, and also x, y, and then other arguments. Okay, so our data is cars, right? So the x variables is speed, right? And the y variable was distance, right? So if I click run, so I can see that so there is a monotonic, it seems that there is a monotonic relationship. So let me add the regression line, reg.line, and so it seems like yes, so as the x increases, y never decreases. So there is a monotonic relationship between x and y. So the next step is that we have to set the null hypothesis, so we can use the Spearman rank correlation. So the null hypothesis states that there is no correlation between ranked speed and ranked distance. Okay, so it only shows the association, correlation between the ranked of each of the variables. Okay, an alternative hypothesis states that there is a significant association or correlation between a significant correlation between ranked speed and ranked distance. Okay, so again we have to use this test, cor.test. So let me type a Spearman here, Spearman, and so we have to use cor.test. So we have to put the first variable, which was cars, and speed, and also the second variable, which was cars distance. And here the method, don't forget that the method has to be Spearman, right? And when you click run, so you will see that Spearman rank correlation, the p-value is very small, it's less than 0.05, so it rejects the null hypothesis. So we accept the alternative hypothesis. There is a significant correlation between ranked speed and ranked distance. And if you look at the value for the correlation, for the coefficient, so it is 83. So there is the value is very close to 1. So there is a strong positive association between the ranked speed and ranked distance. So it also shows that it cannot compute the exact p-value. So we can we can set the exact parameter to false to have an approximation of the p-value. So here you will not get the error anymore. And also similar to the Pearson product, we can also here we can set the COR method as Spearman and COR coefficient as, so let me COR method as Spearman, and also COR dot coefficient, because I want to have the as true. And also we can set the confidence interval here, so the gray area shows a 95% confidence interval to true. Okay, so conf.int as true, comma, and then when we run that this one, so you can see that it shows you the correlation coefficient, which is a very strong positive correlation between speed and distance, and it is significant correlation between these two variables.